What's up, friends? So we're still on Desmos here right now. That's just with our next topic. We're talking about the idea of critical points and inflection points, maximums and minimums. And so I thought the graph would be really helpful for that again. And so what a critical point is. So so given some function, let C be the critical point. So it's when the function evaluated at that point, when its derivative is equal to 0. And so that means that the tangent line is going to be horizontal at that point, right? That means that the rate of change is 0. And these critical points are what we suspect maximums or minimums might be at. So the maximums or the minimums, those are the local optimization points. And and we know that, if something is turning upward, then there's going to be that maximum point right there which has a flat tangent line. And it's going to be the same thing if we have some function and it turns downward, then we know the minimum point there is, again, it's gonna be at one of these critical points. So let's look at like an example of like a function where we'd be interested to see where its maximums or minimums are. So let's look at f of x equals x squared minus 1, and all of this is cubed. So we're going to try and first identify where the critical points are. And that is when this function's derivative is equal to 0. So first thing you do is you take the derivative. So for this one, we're going to need to use the chain rule. So I'm going to knock that 3 down. X squared minus 1, and all this is squared. And then I multiply it by the derivative of the inside, which is 2x, which means that I can just more simply write this as 6x times x squared minus 1 squared. And so when is this going to be equal to 0? Well, we have a couple options here. So when this is 0, so that would be when x equals 0. So x equals 0 is our first identified critical point. And then now it's going to be when this one is going to be equal to 0. So this is the difference of squares. This is x minus 1 times x plus 1. So that means that -1 and +1 are our other two critical points. And so now that we know what the critical points are, there's different ways in which we can tell if it's going to be a maximum or a minimum. So the first way is just to look at the intervals. Is to look at the intervals between each critical point. So when x is less than -1, when x is in between -1 and 0, when x is in between 0 and 1, and when x is larger than 1. And you want to see what is the sign of the derivative. Because remember, that sign of the derivative tells you if that function is increasing or decreasing. And so if the derivative is positive, that means it's going up. So if it's going from positive to negative, that means it's going from increasing to decreasing, which means it's a maximum. If it's going from negative to positive, that means it's going from decreasing to increasing, which means it's a minimum. And so that's kind of what we're looking for. So look at this. So when x is less than -1, so we have something negative times something being squared. So it's just going to be negative. So that means that it's decreasing in this region. When x is is in between that, we still have something negative times something being squared, so times something positive, so we still have something decreasing. So that means that first one is not like, it's not a turning point. It's not going to be a maximum or a minimum. Um, and how about this middle one? So we know that's negative here. What about here? We have something positive times something positive. So boom, boom. So it'll be going up, up. And so that means the only turning point we have right here is in the middle, is at the critical point 0. That's going to be our local minimum. And just looking at the shape of this function, that would also be our absolute minimum. Since we know that it's decreasing, 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 it'll get here, increase, increase, increase. So so we know that that'll be our absolute minimum because nowhere is it going to be lower than that. However, these critical points don't necessarily give you an absolute because maybe the function just shoots off up towards infinity. That's not going to be a critical point, but yeah, that's something to keep in mind. So this is one way of figuring out. The other way is just doing what's called the second derivative test. So in the last video, we were talking about the ideas of second derivatives and concavity. Well, we know that if something's a maximum, it must be concave downward. And if it's a minimum, it must be concave upward. So another way that we could do this is just look at the second derivative and see if it's positive or negative. That's called the second derivative test. So, so right now we're going to need to use product rule here. So we'll have 6 times x squared minus 1 squared, and then plus, this will be 6x, but this 2 is getting knocked down, so this is really going to be 12x, x squared minus 1. And so when x equals 0, is this positive or negative? So when x equals 0 at the critical point 0, we have 0 minus 1, so negative 1. So this whole thing is 6 plus 0. So it's 6, it's positive. So at the critical point of 0, we have that second derivative is positive. So that means it must be a minimum. And then what about at the other ones? So when we look at x equals negative 1 or x equals 1, that's going to give us right here, we're going to see that at x equals negative 1, this is going to be 1 minus 1, so this is going to be 0. This is 1 minus 1, so that'll be 0. So this whole thing is going to be 0. And then that's going to be the same thing at x equals 1, because 1 minus 1, so we'll have 0, 0. And so when the second derivative is 0, that's called the inflection point, because that means that the concavity is changing from concave up to concave down. And since the concavity is changing, that can't be like an extrema, right? So that can't have that hump like as a maximum or a minimum. And so that's, yeah, that's the idea there. So let's so we're on Desmo, so let's use it. Let's map what our function actually is now. So x squared plus minus 1 to the 3. So yeah, let's look right there. So that gave us our critical points right there. And we see that this is the only one. So all of these are critical points because they all have that flat tangent line. They all have a rate of change of 0 at these points. However, this is the only one that's a local extrema. This is a local minimum here because its concave is upwards. We see that these are inflection because this one goes from concave down to concave up. This one goes from concave up to concave down. And yeah, and so that's really the main idea when you're asked to solve for like local maximums and minimums is you just want to identify what those critical points are. This is the reasoning behind it. And then from those critical points you have different tests you can do. You can look at those intervals and see if it's increasing and decreasing, or um, you can look at the concavity, and that'll tell you if it's a maximum or a minimum or neither. So so yeah, this is the main idea. This is used a lot in the application for like optimization problems. And so the point that I really want to stress right now that some people get confused about is what exactly is meant by critical point. So the critical point is just that C. The critical point specifically is the X value. So like right here, this is the critical point. The critical point is 0. But if this was an optimization problem, if you're given this and you're like, okay, so what is that minimum? The minimum occurs at the critical point. It occurs when x equals 0, but the minimum itself is -1. So that's something I really want to emphasize to like keep in mind that the extrema is whatever f of c is at that point. That's what the extremal value is. The critical point itself is just that input to the function. What the function is, that's going to be what the local minimum or local maximum is. So that's a point I want to emphasize. I hope that makes it clear. I hope this clarified any confusion. This was educational. Yeah, let me know if there's anything you want me to expand on.